So thank you very much, David. Thank you very much for coming. I'm really very happy to be here. It's a pleasure and an honor too. I'm just very, very happy. So I'm going to tell you about some recent developments about non-equilibrium statistical mechanics in 7 or 8 hours. I cannot cover the whole subject, of course. I gave a colloquium 2 days ago, but don't worry. If you were not there, I will not repeat all the things, but I will use and say again the things I use. So you have the plan, the program. Today I will tell you about reversibility, irreversibility, detail balance, breaking of detail balance, and hopefully, I have prepared 9 pages, I will get to the Galavoti-Cohen fluctuation relation, Galavoti-Cohen theorem, and have a proof of it in one special context. But before going to that, I have to introduce some mathematical techniques, Markov processes, master equations, and detail balance. So let's start. So again, if we want to talk about non-equilibrium, and I said that the other day, non-equilibrium. Oops. Can you read me?
I will try to bring it
on. The general picture is just a rod connected to 2 reservoirs. And this one works very well. Reservoir 1, reservoir 2. And you have some conducting rod which is connecting both of them. So I draw it in 1 dimension, but it could be a 2-dimensional slab, it could be a 3-dimensional solid, whatever. And so if the reservoirs are at the same temperature, thank you very much, same temperature or same potential or same chemical potential, so suppose that the reservoirs they are identical. So I just use the temperature metaphor, T1 is equal to T2. Then, of course, in the long time limit, the whole system reaches equilibrium, thermal equilibrium, and we can use thermodynamics or statistical mechanics to compute whatever we like. We shall start by computing the free energy of the system, F, and then we can deduce from it the state, equation of state. We can study this free energy and look at its analytic behavior. And we know when it's non-analytic anymore that we may have some phase transitions. All this is equilibrium statistical mechanics, and there are many, many things we can study. Exponents and whatever. Okay, one thing which is interesting in the case of thermal equilibrium is that there is no current. The current, let's say the heat current here, if we consider that I'm talking about temperature or electric current, if I was talking about potential, vanishes. So if you put a measurement device here, there will be no average current. But of course there are fluctuations. So if I compute the total energy, Q of T, so the energy or charge or number of particles transported from left to right, from R1 to R2 during time t. Of course, on average, this vanishes because it's at equilibrium. But there are fluctuations, Q squared T, and these fluctuations in the long time limit are linear with time, and there is a diffusion constant which is associated with it. Okay? So this is typical, what I will call Brownian. It's not the same Brownian motion as Brown saw in his microscope, but in essence, it's the same thing. Okay? Thank you very much. Now I can speak for 10 hours, at least. So, this is the equilibrium case. If now they are close to each other, R1 and R2 are a real blackboard with chalk. This would be a real pleasure. But it does not exist anymore. Are close to each other. Maybe red is the best. Close. Which means that the temperature difference between R1 and R2 in relative value is very small. Then we can apply linear response theory. So when I was a student, this was StatMech 3, almost 3 months of, at that time I found it boring because I could not understand that it was very important, but it's very important, linear response theory. So I'm not going to teach StatMech 3, of course. And typically there is a current. There will be a stationary current, heat current or particle current, which will be proportional to the gradient of temperature. Okay, the difference of temperatures between left and right. And this lambda, which is thermal conductivity, will be given, so I hope there may be some mistake here, but you will correct it, but will be related to the fluctuations at equilibrium by a Einstein type of relation. There may be some factors too, maybe some length here, but this is typically what you get. If you know fluctuations at equilibrium, you can compute or deduce conductivity or mobility or susceptibility, call it as you wish. I don't try writing it in French. Mobility, susceptibility, whatever. All these names just tell you about linear response. Okay, and this is already quite a lot. I mean, and this is enough, in fact, for many practical applications. But we'll be interested by something different. We'll be interested here by the case where R1 and R2 are really different, just very different temperatures. So the current is not given by linear response anymore. There could be some gradient cube or whatever, and there is no good theory for that. In fact, we suppose that there is a stationary state. So not always the case. We shall assume it here, that we reach a stationary state. But how can we qualify, how can we characterize this stationary state? For example, in thermodynamics, equilibrium states are given by optima, optimums of entropy, free energy, some minimization procedure, maximization procedure. Here, is there anything like that? We don't know. In thermodynamics, we know that we can characterize the state of the system by a few parameters. Here, out of equilibrium, we do hope it's the same, but we don't know what are the relevant good parameters. Again, in thermodynamics, we have some state functions, good functions to be optimized. Is there anything like that out of equilibrium? This would be nice, but there is no general procedure for constructing a non-equilibrium potential. Although I will tell you about some progress about that and what people believe. I already told you 2 days ago about large deviations. And also here we know that there are fluctuations at equilibrium around zero current. Of course, even if the current is big and non-zero, there are also statistical fluctuations around this non-zero current, and we want to characterize them. Are they still Gaussian, or do we have some new laws, some different laws? Are the fluctuations typically in square root of time, or maybe some non-half exponent, 2/3 or whatever? All these things we want to explore. So the main thing is that as soon as there is a current, a stationary current, which is non-zero, and really non-zero, not infinitesimal, well, this breaks time reversal invariance. If you make a movie, project it backwards, you will say, no, it's wrong. Time reversal invariance. And this is exactly the thing that we want to mathematically explore. What does time reversal invariance mean? And what does breaking time reversal invariance mean? Precisely in mathematical formulas, at least in some framework. So this is today's lecture's aim. what is reversibility, what is irreversibility, and how we can quantify them for Markov processes. So because I use the word Markov process and there are some students around, I will review the dynamics and I will review Markov processes a bit fast, but at least review the things I need today and in the next lectures. And the rest, of course, I will leave it out. You can learn it by yourself or not learn it if you wish. You don't really need that. So what is reversibility and what is irreversibility? And we'll talk about detailed balance. So irreversibility. So we'll start, of course, by reversibility. And detailed balance and large deviations. And large deviations. Large deviations. Okay. So of course we want to describe not only equilibrium, we want to describe dynamics. So if we want to describe the dynamics, I'll be talking mostly of classical systems. If you ask me questions, or I may mention now and then quantum systems, but I would be mostly classical. It's my background and it's easier to explain too. So we consider a classical system with 10 to the power 23 degrees of freedom, a very large number of degrees of freedom, large n. So classically it's moving in a phase space of r to the power 6n dimension. It's huge. And we could study all the trajectories in this very high dimensional space, and it would be very complicated, of course, to follow that. Another way of trying to make things simpler is to use a density in phase space, rho, and write the Liouville equation. So this could be a strategy, which is equivalent, and write the Liouville equation, which is something like d rho dt plus rho Poisson bracket with the Hamiltonian is equal to 0. So this is the strategy which is used, for example, by Kubo for developing linear response. So this is something which is well explored in the 50s and the 60s and later on. But I'm not going to use this strategy. Again, it's extremely complex. It's just a kind of mathematical fake. Now you have a PDE, which is a function. Rho is just a function of position and momentum, but in fact it's perfectly equivalent to 6n ODEs, so it's as complicated as studying the ODEs. In quantum mechanics, you would have here a density matrix and a Lie bracket, so you can also do the same. And Kubo, in his classic paper about linear response, really treated the two dynamics, classical and quantum, in parallel. So it was extremely elegant. So we want to reduce the complexity of this thing. It's too complex. And to reduce the complexity, I will use, so there are many ways. And the fact that I'm using one framework, so this is something important I want to emphasize. The fact I will be using one framework, which is the Markovian, I'm going to explain that, framework, doesn't mean that what I'm going to say only applies to Markov processes. It's just a framework. But some people prefer to use Langevin type of framework. Some people, and I'm not at all a specialist, use some other schemes, especially people who do molecular dynamics. They use thermostat, Nose-Hoover, whatever. I know almost nothing about this, so I will be Markovian. But again, I emphasize the fact that what I say goes beyond Markov. Okay? But I will prove things in the Markov framework. So what is a Markov? So we shall use a coarse-grained dynamics, because I want to understand the dynamics of a system, not only the equilibrium. So the coarse-grained dynamics will use a Markov process description. And I will just review this very quickly. What are we going to say and do? We say that the system exists in some configurations. So we enumerate, we just list the microscopic configurations of the system, the coarse-grained micro or macro or meso configurations of the system. So I suppose, but again, this is not a restriction, that there is a kind of numerable number. So I call them C1, C2, Cn. N can be finite, infinite, or N can be even continuous. It could be a position in space. But just think, it's easier to think of a system of, I don't know, spins or particles in a box of a finite size, and you can put one particle in this first box, another particle in another box, some finite thing. But it could be more complicated than that. Is it okay? Or a random walker on a finite lattice, so it could be on site 1, 2, n, and here are other configurations. Of course, it can be much more complicated than that, but think of a finite number. And then we define transition rates. So transition rates which tell you that a particle hops, the system hops, the system goes from configuration C to C prime during interval of time dt between t and t plus dt. The system jumps from its micro configuration C to the micro configuration C prime with probability m of C towards C prime dt. So it's just like, radioactive decay. We all learned that in high school for just a radioactive particle which decays with lambda dt. But here you can go from a configuration to another with different rates. And the most important hypothesis is the Markovian, because here I did not use this concept, but it's the most important hypothesis is that this jump rate here, m of Cc prime, this jump rate does not depend on the previous history. So no matter on how you got into C at time t, your jumping rate from C to C prime is not influenced by your past. This is extremely important. It looks, like a very innocuous hypothesis, but it's very strong. It does not depend on the past history. So everything somehow starts anew at time t. You are somewhere, and the fact that your random walker jumps from site I to site I plus 1 does not depend on the fact that you've been waiting at I for a long time and doing nothing, or you just arrived from I minus 1. It does not change anything. Okay? No memory of the past. This is extremely important. Once we have that...
So you're emphasizing this from obvious reasons, this assumption, but then just 10 minutes ago you told us that what you're going to derive will actually apply even beyond the Markovian scheme.
Yes.
So how am I supposed to make the connection? We're making a strong assumption that
yes.
The results we expect will be contingent on this assumption.
Because I'm going to prove things using Markov equations. So if you're non-Markovian, one easy answer to your question is that if I have a finite time, finite decay, then somehow I have a kind of kernel, and I can, for example, Kubo proved his equation, his relations, also for integral differential Langevin equation with a kernel which decays fast. So if you have a memory, but a memory which lasts 1 hour, it's okay. There's another mathematical escape for your question. You can always, almost always, find a Markovian embedding. I mean, if you start adding some degrees of freedom into your system, you can always embed your system into a more complex one, which becomes Markovian. Of course, but this would be a kind of a stupid answer. If I go back to Hamilton, I'm Markovian. I don't want to go back to Hamilton, so I have to find a trade-off between the coarse graining, which reduces the complexity and the number of degrees of freedom, and the Markovian hypothesis. So it means precisely that the dt here is not zero, it's not an infinitesimal, but it's in fact delta t, and this delta t is bigger than any smaller relaxation time that you have inside your system. So there is some physics hidden here. Even in Brownian motion, somehow after one collision and before the next one, the particle forgets about correlations. And I think in Einstein's paper 1903, this is stated already. So dt is not a mathematical dt, although we'll consider it like that. It's a dt which is big enough so that the system has forgotten about internal memory. Okay. Yes?
In relation to that previous question, so in what sense it is necessary to do this coarse graining in this procedure?
Oh yes, repeat the question. So in what sense it's important to do the coarse graining? Well, the idea is there are some technical things. For example, I'm going to prove Galavoti-Cohen, and Galavoti-Cohen relies in some kind of mixing. Okay? So they in fact proved their theorem first for a Hamiltonian dynamical system, but which is Anosov, which is chaotic enough so that there is some mixing, and they can prove that some invariant measure exists and so on and so on. As soon as we go to stochastic systems, this is guaranteed. You have stochasticity or Langevin, which allows you to have mixing, so it becomes much simpler. Then it's also true that for us physicists, having a Langevin equation or Markov process for a random walker is something very natural. So it's a good model, unless proven otherwise. So let's continue. Time is flying, as usual. I'm going to write the Markov equation. I was thinking to prove it, but maybe a bit long, so I'll just refer to books, because I think this is standard material, and probably most of you already learned about it. So once you have a Markov process, you can define the probability of being in a configuration at a given time t. And you can, just by writing a balance equation, you can write an equation for the time dynamics. How does this probability of being, that's wonderful, thank you very much, in configuration C at time t evolve? Intuitively, it's very easy. If you want to do it more mathematically, it takes more time. Well, you just count how many configurations evolved towards C. So the balance is positive for configurations coming towards C. So C prime evolving towards C. And the balance is negative if you go away from C. So you're leaving C. So again, I thought I was going to prove this equation, but maybe I will not. I can just give you some references. The standard book is von Kampen. Von Kampen. Or Risken, or Gardiner, whatever you like. This is proved. Any question about this equation? It's quite natural, okay? You just count what's coming in and going out. Okay, this equation, you can write it in a, thank you, in a more formal way, as a matrix, okay? So you see, it's a graph, in fact. I have configurations in the graph of my configuration space, and I have some configurations which are evolving to C, and C is evolving out to other configurations or to the same ones, can evolve back to C prime, and so on. Okay? So you can represent this as a matrix. In fact, you can write it as dp dt is a matrix times P. Looks like a Schrödinger equation, but the matrix doesn't have to be Hermitian or anything like that. So what will be the matrix M? Well, the non-diagonal entries will be the rates, just M with just M C1 to C2, just to change the notation, C to C prime. Okay, it's just, but you have to be careful about the diagonal entries. The diagonal entry entries. Well, the only thing is that you have to rename this object. You have to call it as a diagonal term. Then you see we'll have a perfect matrix equation. So you have to be careful, there's a minus sign. So the diagonal entry MCC is minus the exit rate from C to any other possible configuration it connects to. So the diagonal terms of my Markov matrix are the opposite of the sum of all the exit rates from C to anywhere else. And then you have a nice equation. And just to save some time, I can leave you as an exercise. Exercise 1. Easy one. I have an infinite line, discrete line, the numbers Z, 0, 1, I, and I have a random walker which is asymmetric, which works with P and Q. So you have an infinite matrix, so write M for this random walk. Okay? Exercise 2. So I told you that I would be considering Markov processes with finite number or numerable number of configurations, and I'm of course going to contradict myself immediately. So I consider now a continuous space. So in one dimension, but it could be in any dimension, of a particle x with velocity v. And I write Newton's equations. So x dot dx dt is v. And m dv dt. The particle is subject to some damping, minus gamma v. There is some external potential, let's say harmonic or whatever, anharmonic, whatever you like. And I add to that, so this is just Newton equation, okay? Second principle, third principle of Newton, second. But I add to that a random force. This is what Langevin did. So it's a force, which is a statistical force. You don't know exactly what it is. The only thing you know about it is that it has an average which is 0 at any time. And it has very short correlations, but very strong correlation at the same time. So you express it like that. 2 gamma delta of t minus t prime. So very strong percussion, but at a given time, and then you forget. This is a Langevin equation. So it's the analogous of what we described, but now x and v can be continuous. So you have to define a probability distribution at time t of being at position x and having a velocity v. And the analogous of the Markov equation here has a different name. So it's not Markov, it's called Fokker-Planck. It's in fact exactly the same thing in continuous space. That is for physicists. For mathematicians, it's a different game because you have to go to operators and so on. And the Markov equation, the Fokker-Planck equation, is given by this PDE This is just a transport term which would come from Liouville equation, but of course there is an important addendum coming from diffusion, from the noise, which induces diffusion, and which is of course at the heart of the whole business. Okay. So, often, again, imagine that many people are familiar with that. This is just another framework. In many, many cases, you neglect inertia. So m is 0. And then you get a first order. You just say that v is x dot. So you get a first order Langevin equation. If I substitute that, I will have x dot is 1 minus 1 over gamma gradient u plus 1 over gamma psi. And this is a very good equation to study fluctuations, thermal fluctuations, and so on. So if you consider this equation, is it okay? I'm not going too fast? Yeah? If you consider this equation, you can write a Fokker-Planck equation associated with it, which will be dp dt. So now it's p only of x. I'm forgetting about the velocity. Is equal to d dx gradient u over gamma p plus gamma over gamma square d2p dx2. So it's a much simpler equation than this one because it contains only one variable. And one exercise I leave to you is that using this equation, show that x squared from this equation grows linearly with time, and it grows like 2 gamma over gamma square t. So I'll give you the trick if you don't. Sorry, without a potential, of course. Free Brownian motion for u equal to 0, of course. Sorry for that. Thank you. So for free Brownian motion, we have if u equal to 0. You have a linear drift of x. So the idea is simple. Just multiply by x squared on both sides, integrate by parts, and you will see that ddt of x squared grows like ddt of x squared is given by 2 gamma over gamma squared. Okay? So you get Brownian motion from this equation. This is Langevin's point of view. Okay. All this is explained in these books. Von Kampen, Risken, Gardiner, whatever. Oui?
How come you don't need to specify the whole distribution of the noise and only its parameters?
Good question. I was too fast on it. You assume that Xi is Gaussian. And if Xi is Gaussian, if you know the first two cumulants, well, there are no other cumulants, you know the whole distribution by using Wick theorem, for example.
Otherwise you get a different focus.
Of course. So Xi is Gaussian. Yeah, I don't want to enter into these details, but it's a very important question. Yeah. Sorry for being a bit loosey about that.
Where did you enter
The Gaussianity?
Yes.
If it were not Gaussian, I would have a whole series of higher derivatives. In fact, fourth cumulant, Gaussian has zero fourth cumulant. But if I had a fourth cumulant, I would have a fourth cumulant times the fourth derivative, sixth cumulant, sixth derivative. If I had any noise, I would not even have a PDE. I would have a formal thing with infinite number of derivatives. Well, some people play with that too. I mean, things can be done. I mean, there are many, many papers, for example, by Peter Henke, who has worked a lot on these things, and it's not totally hopeless, though it is quite hopeless. But anyway. So this is, by the way, Langevin's derivation. Langevin wrote Langevin equation to obtain Einstein's diffusion, Einstein's Brownian analysis of Brownian motion, starting from mechanical equations. Einstein had rather a kind of statistical point of view. Okay.
But in Langevin equation, you do not really need the Gaussianity of the noise.
No, you're right. You're right. But I think, because Langevin didn't even assume it. No, you're right. But to write Fokker-Planck, I absolutely do need. So the way I explained it by multiplying by x squared and so on, I needed it.
No, but if eventually you want to explain Brownian motion, just the version, that's only the second moment. So
Yes, because if I had a fourth derivative, I multiply x squared, for example.
Didn't care about.
Yeah, in fact, Langevin, didn't even write. If you look at his paper, which is just 1 page long, he just manipulated the Newton equation by taking integration by parts and so on. It's very subtle and it works. Yeah. But to write Fokker-Planck, you need Gaussianity. So let's now connect to thermodynamics. So I have my Markov equation here. And first, I'm not interested in non-equilibrium systems. I'm just interested in equilibrium dynamics. Well, one thing I know to describe equilibrium, at least, what I need to have is that the stationary state of this equation, which means this derivative equal to 0, the stationary state has to be the thermodynamic state given by Gibbs-Boltzmann canonical law. Okay? So what we need to have at equilibrium at temperature T, we need that the stationary probability of a configuration is precisely given by Gibbs-Boltzmann. So if a configuration C has an energy E of C, KB is Boltzmann constant. Very often I will, of course, use beta. This one should minus beta E. It's easier to write. Beta is 1 over KT. Okay, so what does it mean? It means that we have to substitute Boltzmann laws here, and this gives you a very nice identity. The fact that I can always simplify by the denominator. And this is true, of course, for every configuration. Because I have, if n is the number of configurations, I have n equations like that. So I will have n equations like that. So this equation, which is again a bit trivial, but it's a constraint. It's a constraint on the rates. And this is a global constraint. So it's called global balance. It's a constraint on the rates. They cannot be completely arbitrary. They have to satisfy, in order to describe thermal equilibrium, they have to satisfy this constraint. So how many rates do I have? Well, n squared minus n, because the diagonal rates are in fact constructed from the others. So my matrix is at most n squared minus n independent rates, and I have n constraints. So I have n constraints over n squared. It's not heavy. I mean, it's not much. Okay. But okay, it's already there. So I, of course, removed it. If you go back to Langevin equation, which I wrote a few minutes before, let's say the one only for x, or for x and v, you know the distribution at equilibrium. It's Maxwell's law. Okay? It's exponential minus beta u of x minus beta half mv squared. You know that this has to be the equilibrium distribution. So if you plug it back into Fokker-Planck, this will give you a constraint in order to have Maxwell distribution, or Maxwell-Boltzmann Gibbs distribution, to be a stationary distribution of Fokker-Planck. The strength of the noise, which I call capital gamma, has to be specific. Okay? And it will give you the following equation. So I leave it as an exercise. This will tell you, in the case of Langevin, this will tell you that the strength of the noise, in order to have this stationary measure, has to be kT times small gamma, which was the dissipation, which was the friction rate. So the strength of the noise is constrained by temperature and dissipation rate. This is in fact nothing but an avatar of Einstein fluctuation and dissipation relation. In some books it's called the first fluctuation dissipation relation. Okay? And before I told you that x squared grows like 2d times t times the time, and d was given by gamma over gamma square times t. But gamma was unknown. It was something we put from nowhere, the strength of the noise. But now we know it is gamma. Okay? So if you plug this back, it just gives you that, in fact, so this is by definition 2 dt, and d, the diffusion constant, is given by kt over gamma. All this is very standard, but this is Langevin's way of reconstructing. This is Einstein relation. Okay. This is really Einstein relation between friction, temperature, and diffusion. So it's a very short way of reconstructing it. Okay.
Sorry, Kirone?
Yes?
The end constraints that you got, I can put in any stationary measure and get end constraints. Right?
Yes, but I want,
So here
yeah.
we're still not making use of, like, deep use of the fact that it's the Boltzmann measure.
You're right. If I constrain my stationary measure to be something, I have a constraint. But if I want to connect with thermodynamics, this stationary measure has to be Boltzmann's measure, Gibbs, Boltzmann, Maxwell, canonical measure. And this gives you, for example, in the case of Brownian motion, this fixes the amplitude of the noise and gives you back Einstein relation. So I use the fact that I know the stationary measure, and it's given by Boltzmann, Gibbs.
But that doesn't.
But it could be another one.
Balance, right?
I'm coming to detailed balance. This is global balance. So now let's get to the interesting things.
Is there an analogy to the Einstein relation in the discrete case that you
Yes, it's exactly the same. In fact, it's exactly the same thing. If you just discretize, for example, Langevin equation, you get a discrete. It's just exactly the same thing.
No, but I'm asking here, what would be the strength? What would be the analogy of the?
The strength of the noise.
Yeah.
Okay, I will have to think about it. In fact, this equation is the analogous of Fokker-Planck, so there is no noise apparent to it. You can write a stochastic equation by introducing some Poisson process. So this will fix you the rate of the Poisson process. In fact, you see, Langevin equation goes to Fokker-Planck. Fokker-Planck is the same as Markov. But I didn't tell you what is the stochastic process, the discrete stochastic process, the hopping process. So you will have to put some Markov generator and so on, some Poisson generator and so on. But yeah, and then this will fix some constraint on the rate of this Poisson process. Yeah, but it's going too far. Okay, so now I'm coming to detailed balance. The word was pronounced, and this is the important thing. So now let's go to reversibility and detailed balance. I can remove that. Maybe time for a pause, or are you tired, or am I tired? You want to pause, you don't want to pause, you decide. I can continue, we can go on, but or pause later, or never. No lunch. I go on. Okay. Let's go on, because the beginning is easy and not too tiring. So, now we arrive to detailed balance, and this is the important thing. So this is reversibility and detailed balance. This is the second. So for the moment being, we just have a global constraint, which has global balance, but there is something much, much stronger than that. And the point is, here I'm lucky I can manipulate this equation. So this is the Markov equation. I will just transform it a bit. First of all, I have a double sum, but I can use just one sum. So I can just put everything under one sum, and I'm not modifying anything. Thank you. Unfortunately, I have only 2 hands, but I'm not like Shiva. I would like to. No offense to my Indian compatriots, of course. So I just rewrote the equation like that. It's the same one. And by the way, I don't even need to say that C prime is different from C now. Okay, because twice the same term. So now it's a very neat equation. And suppose I want to be in the stationary state. So this is 0 as stationarity. Well, then a very easy way to have a 0 is that each of the terms in the brackets vanishes separately. Okay? So automatically, if I have the condition that M of C prime of C, P of C prime, P stat is equal to, of course, it's asking for much, much, much too much, but if I have that, I'm happy. I'm automatically in the stationary state. Okay? So this is, of course, I'm going to explain all that. This is extremely important. This condition, which implies stationarity, but it's a very, very strong condition, because here we have n squared over 2 relations, approximately maybe nn minus 1 over 2. This is called detailed balance. So we are going to explore what it means and to qualify that in details. So first of all, naively, what does this quantity represent, this difference? Well, it tells you the probability current from going to C prime to C minus the probability current from going to C to C prime. So if I have 2 configurations, C prime and C, I have a probability current from going from left to right and the probability current from going to right to left, C to C prime. And if this vanishes, it means that every couple of configuration is somehow balanced separately. So it's a global, it's a detailed 2x2 balance, but it's not required. We could have a stationary state in which, of course, we could have a much more complex. I mean, if the sum of n terms is 0, doesn't mean that each term has to be 0, of course. There can be compensations. But at least it means that the local current vanishes. But this is much, much more important than that, and this is what I'm going to prove now. It's a very classical but very nice proof. In fact, and this was discovered, of course, by Onsager in 1931, and this is the core of his reciprocity relations, and it led him to the Nobel Prize. Detailed balance is equivalent to time reversibility. So it's a symmetry of the system. Okay. So in fact, what we are going to do is to construct, we shall construct a probability measure, a probabilistic description. Maybe it's less pedantic. But it really means a probability measure of the trajectories of the systems, of the histories. So we are, in fact, building a path integral without saying it. So we have to know 2 things, which are very, very elementary, and again go to high school physics. First of all, what is the probability of remaining in a configuration C during some time, a time tau. Well, let's compute it. So we have a time tau, let's see, from t to t plus tau, from 0 to tau. What is the probability that I don't move? Well, I will just cut my interval tau in small intervals dt. Okay, I will have tau over dt, small intervals like that. And what I want is that in each of these small intervals, I don't move. I don't leave C. So what is the probability of not leaving my configuration C between t and t plus dt? It's 1 minus the probability of leaving it, so going somewhere. Okay, that's the probability of not leaving it between t and t plus dt. I go nowhere. Is it clear? Okay. Now I use independence, so I'm not leaving between t and t plus dt, t plus dt, t plus 2 dt, and so on and so on. How many intervals do I have? T over tau over dt. I let dt go to 0, so this gives me that the probability of not leaving configuration C is given by that, times tau, just the exponential. Okay? But if you remember well, I precisely define, I minus the exit rate, I define the diagonal term of my matrix. So by definition, this is exponential MCC tau. MCC is negative. Okay? You remember that? That's the first point. The second point, which is trivial, is in the definition. What is the probability of going from C to C prime in dt? Well, by definition of my Markov process, etc., it's m of C to C prime dt. Okay? So now I will consider a history of my system. What should I... What can I remove from here? I want to keep that. So I consider that I do some experiment which lasts a time capital T, and I look at what my system is doing during that time. So my system is in the stationary state, and I start somewhere. So I'm just, I'm making a movie of my system between time 0 and time capital T. So it's not a temperature, it's a final time. And my system is doing something. My system is evolving. It's starting at configuration C0. Then at time T1, it jumps to a configuration C1. Then at time T2, it jumps. So it's a kind of sketch, of course. I'm representing, kind of states, C1, C2. They're not necessarily energy states, and so on. And at time Tn, it reaches the last state, I don't know, which can be the same. Of course, it's just like a random walker. It's somewhere, goes somewhere else, come back, and so on. Okay? So what is the probability of this trajectory? So this is a time-dependent trajectory. I call it C of t. T between t and t final. What is the probability of seeing it? Well, I pick up the starting point with the stationary state, P stat of C0. Okay? Then I remain in C0 during time T1. So it's exponential m of C0, C0, T1. Then I jump to C1. So it's m C0 to C1 dt1. Then I remain in C1 during time T2 minus T1. T2 minus T1. Do you follow me? Then I jump from C1 to C2, dt1, and so on. And I continue like that. So if I were really pedagogical, I would put things in colors and so on. So the jumps, I put them in red, and so on. So the last jump I have is from Cn minus 1 to Cn, dtn minus 1, dtn, and then I remain in Cn during the time I'm left. So time t minus tn, I remain in Cn. Okay, I put it only once, m of Cn, Cn. Okay? So this is the probability of seeing this path. In fact, this is a path integral that we are doing here. We are putting a measure on this path. Okay, that's a path. But from this path, I can construct another one. And of course, on the blackboard, it's not so easy to do it very finely. But this is a story, history. But I can project my movie backwards. So I can consider the trajectory c of final time. It's not a temperature, it's a final time, minus t. So I project it backwards. So it means that at time t equal to 0, I'm now started with Cn. At time t minus Tn, I jump at Cn minus 1. Okay? I'm just tracing the function c, capital T min. I will end up at time t at C0. And the last jump will be at t minus T1 from C1 to C0. C1 was higher. So I'm tracing, I'm sketching the time reverse trajectory. Okay? I can very well ask what is the probability of seeing, so I call it C change of t. C, I don't know what, yeah, C with something on it. So there's a time reverse trajectory. Call it whatever you like. Okay, it's a bona fide trajectory by itself. I don't have to say that I constructed it from the previous one. It's a trajectory. So I can try to compute its measure, its likelihood to appear. Well, I have to choose P stat of Cn. I have to remain in Cn during time t minus Tn. I have to jump from Cn to Cn minus 1. And so on. Do sometime dt. I have to remain in Cn minus 1, and I continue. I just measure the probability of this whole trajectory, and I want to write the right term, and I just copy on my notebook, because otherwise I will make a mistake. So I have to remain in the last one during a time t1. And the very last jump is from C1 to C0. And you can fill the blanks by yourself. Okay. So now how do I quantify reversibility? Well, I just make the ratio between these two probabilities. So reversibility or irreversibility. So I use that, of course, in writing the measure. I just try to see how much bizarre it will sound or look if I project my movie backwards. And this bizarreness, this oddity, will be measured by making the ratios of these two probabilities. The probability of seeing C of t divided by the probability of seeing C hat of t, C chet of t. Well, if you look now at what's written on the blackboard, you will first see that all the pause times, the time that you remain somewhere, which are in the exponential, they're exactly the same. The time that you spend in CI in the forward history, or that you spend in CI in the backward history, they're exactly Ti minus Ti minus 1, or Ti plus 1 minus Ti, the same. All the exponentials, when you make the ratio, will cancel each other. Okay? So what you have left, what you're left with, is just P stat of C0 times, okay, I will not use colors, or M of C0 C1, M of C1 C2, blah blah blah, M of Cn minus 1 Cn, divided by, and I write it backwards, P stat of Cn and all the opposite jumps, M of Cn to Cn minus 1, M of Cn minus 1 to Cn minus 2, M of C1 to C0. Okay? And now we are done, because now we are going to use detailed balance. We are going to use this relation recursively. So I use it here. What does it tell me? That I can swap through this P stat through this matrix element at the condition of switching C0 and C1. So this is equal to P stat of C1, M of C1, C0. But now P stat of C1, I can bang it against C1, C2. I swap them, and I have a P of C2. So I will zip this thing through. All the indices here will be reversed, and my P stat of C0 will become P stat of Cn. So this is 1. Okay? Everybody followed? By using recursively detailed balance, I show that the ratio of seeing a given trajectory with seeing the time reverse trajectory is equal to 1. So detailed balance implies time reversibility. And the contraposé is true too, because you just use this thing for just a trajectory which is very simple, which goes from C to C prime at any arbitrary time, and just say that this trajectory is time reversible. So it will just give you the ratio between two guys and just gives you detailed balance. So it's the other side is trivially true. Any question about that?
Yes. To only you assume detailed balance and go to reversibility.
Yeah.
It is incorrect to think about it the other way.
No, I can prove it. If I suppose that I'm time reversible, I just take a trajectory like that. I start at 0, at time t over 2, I go from C to C prime, I end at t.
Yeah,
And if I just say that it has...
If you assume detailed balance, you will get time reversibility.
That's what I prove here.
Yeah.
Mm-hmm.
You did not show that detailed balance is necessary for that.
So I said it very rapidly, but I say that now suppose I have time reversibility. Suppose I have it. I consider this trajectory, a trajectory which stays half of the time in C, and then jumps to C prime and stays there. I reverse it. And I say that I have time reversibility, so the other trajectory is equally likely. Same probability. C prime, T over 2, C. So I suppose that these two trajectories have the same weight. Okay? Well then, it just tells me that M of C to C prime, P of C, divided by M of C prime to C, P of C prime. This is the weight of this trajectory. I'm forgetting about the exponentials because they will cancel out. This is the weight of the other one, If it's reversible, it has to be equal to 1, and this is detailed balance.
So should I understand from that if, say, quantum dynamics is unitarian, that automatically implies detailed balance?
Well, it's a hard question. I'm proving things for this Markov process. It can be true also for Langevin process. I know it's true, for example, for Lindblad equations, which are quantum Markov processes. I think that unitarity implies detailed balance, but I'm not sure. I mean, I will have to think about it. But if you give me a precise framework, I can give a precise answer. For example, Lindblad. If you assume detailed balance inside your Lindblad equation, it's reversible.
The funny part here is that in classical physics, let's not talk about unitarity, just reversibility of equations of motion.
Yeah.
That kind of imply the detailed balance. I cannot get rid of the feeling that the equations of motions themselves do not obviously contain thermodynamic equilibrium. So where those probabilities came from, it's not a proof of equilibrium thermodynamics. So
No, but here I just suppose detailed balance. I don't suppose any equilibrium thermodynamics. I just say that this bizarre condition, which was like asking too much, is equivalent to reversibility in the mathematical sense of the Markov process. A trajectory has exactly the same probability as the time reverse trajectory. So you cannot distinguish past from future in such a Markov process. Yeah?
Here you prove that in an equilibrium, you take only trajectories probability in equilibrium, right? In equilibrium state.
Okay, I didn't use the word equilibrium.
No, P stat.
But you're right, it's...
What P stat?
It's P stat.
You compare two trajectories starting from equilibrium state. Yes.
Yeah, so
Okay.
stationary state. Yeah, that's important.
Stationary state.
But in fact, you're right, because you're not confusing things. You're just trying to say what I'm going to say. I'll answer your question later, just in a second. Here, it's a mathematical proof. I have a Markov process with a stationary probability which satisfies this bizarre relation. I'm not talking about Gibbs, Clausius, Joule, or Boltzmann. It's disconnected from thermodynamics. In fact, it's even a chapter of Markov processes, which they call reversible, time reversal. And if I have this property, then each history has the same likelihood to happen as the time reverse history. It's a kosher mathematical proof. Okay? Now let's go to equilibrium, because this is the main point. So that's precisely what you said. Now the folklore goes like that. We know that Hamilton equations are reversible, that mechanics is reversible, or Schrödinger equations are reversible. So we know that thermodynamic equilibrium is reversible. But reversibility is equivalent to this detailed balance condition. So it means that if I replace now P stationary by P equilibrium, this is also true. So it means that the Markov rates have to satisfy detailed balance with respect to Gibbs-Boltzmann measure. Not any measure, but the equilibrium measure. Because we know that equilibrium is time reversal invariant. But if in some other process, some other stationary state would be time reversal invariant and not Gibbs, I don't know, whatever, I mean, another one, then it will be true also.
I lost it. You said that Hamilton is time reversible.
Yes, equilibrium is time reversible. So it means that any good Markovian description of equilibrium thermodynamics has to satisfy detailed balance with respect to the Gibbs-Boltzmann measure.
And vice versa. Suppose the Hamiltonian is a particle subjected to external magnetic field.
Okay, so I'm not breaking time reversal invariance to rotation or
thermal equilibrium.
yes. So then I will have some minus signs coming on, and yeah, I have to be careful with that. Yes,
So the other
I will
one-
have to reverse my magnetic field. So I have some rates which depend on B, and I will have to put some minus B somewhere. Or if I have an omega rotation vector, I will have to put some minus omega. And if you remember,
What I think the vice versa is not true. The fact that they are reaching thermal equilibrium does not mean the Hamiltonian is time reversal.
well, it's covariant with time reversal. If you change B into minus B,
Yeah,
you
but
get the
if
same
I don't-
dynamics.
If I don't change,
If you don't know, but
right, it's external power.
yes, but I will have to change it here also, my external parameter. If you remember on Sager's identities, it's Lij of
Yeah.
B omega is L plus epsilon plus or minuses, Lji of minus B minus omega. And if it depends, you have to put the signs and so on. You had a question.
Yes, I think I missed something technical. So you said earlier that as you take the ratio, all the exponents will cancel.
Yeah.
I'm missing that because, say, on the right-hand side, the intervals are the same, but the rates are different. So you have, on the right-hand side...
The remaining rates are the same. The rates to remain there, they are the same. They're just the rates of not going elsewhere.
But you have T1 times M
Of C1, C1.
C1.
Yes.
But over there you have T1 times M of C0, C0.
Yeah, but it will also appear, because I didn't write it here, but it's here. I promise you. Just redo it slowly, don't worry. It takes a bit of time, but I did it very fast. But if you just redo it, you will see that exactly, because I mean, you're staying in C0 here. Of course it will. I'm staying in C0 here, and I'm staying in C0 here, for the same duration. So it will cancel. And I'm staying in C1 here, I'm staying in C1 here, for the same duration. I needed to do it many, many times myself, before being convinced. It works. There is no cheat. There is no cheat. Do we still have a little time? Yeah, we do. Okay. So, but it's very interesting, all these discussions, because it's precisely what I want to talk about. So it was not clear before, I would say till 20 years ago, this difference between stationary and equilibrium was a bit fuzzy. Okay? It's true that equilibrium state had the property of detailed balance because of the underlying time reversal symmetry. But you could very well have some other stationary states which would be time reversal invariant and which would not be equilibrium. So things have changed. Things change. Now, people consider that detailed balance, and this is a strong, but this is a change of nomenclature. Detailed balance. So if you have suppose you have a stationary state. With detailed balance. Well, in fact, now people really call it equilibrium. This has become a definition of equilibrium. Equilibrium is a stationary state which is time reversal invariant. Okay, it's like that. So because otherwise, equilibrium is a bizarre thing to define. How do you define it? So that's an operational way of defining it properly. Okay? Okay, now I want to go to non-equilibrium. Finally. So to go to non-equilibrium, which means something which is not time reversal invariant, something which is not reversible, irreversible, so we have to break detailed balance. So non-equilibrium is breaking of detailed balance. And the thing I want to tell you in the last 20 minutes or so, I hope I will have time. And this is really the message of the first lecture, is that for a mathematician, detailed balance can be broken in any way. You just take a Markov matrix which doesn't satisfy detailed balance and you're happy. But not for a physicist. For a physicist, because the underlying equations, I'm forgetting about magnetic fields, I'm forgetting about beta decay and parity violation, whatever. For a classical naive physicist, Hamilton equations or Schrödinger equation is time reversal invariant. Okay? So physics is time reversal invariant to a certain extent. So this breaking of detailed balance is not arbitrary. Something remains of the underlying absolute time reversal invariance. And this is the way this equation is broken out of equilibrium that brings you all these work theorems, all these Galavoti-Cohen relations, and so on and so on. So this is what I want to explain now. But before doing that, I planned, but time is flowing fast, I planned to talk a bit about large deviations. But did everybody attend my colloquium, more or less? Or more or less? More. Because I cannot spend half an hour on large deviations, but I need large deviations to introduce the breaking of detailed balance. Or maybe not. Okay, maybe I will do a time reversal of my lecture. Yeah, I will do that. Okay, I'll tell you about large deviation later. So recall large deviations. And if you don't, well, I was planning to tell you about large deviations first, and then breaking of detailed balance, and then put things together, but I will do it on the other way around. So I'll come back to large deviations on Thursday. So now let's go to breaking of detailed balance. So the question is there a natural way of breaking detailed balance? A physical way? Because again, a mathematician would just say, take an arbitrary Markov operator, matrix, it will break detailed balance. But we don't want that. So yeah, because I need all this, so yeah. So yes, there is. And I will give you an example, always the same example. I will take a system which is connected with two reservoirs at temperature T1 and T2. So now, first suppose that the system is at equilibrium, so T1 equal to T2. Then I can spell out detailed balance in the following way. Exponential minus 1 over kt, T1 equal to T2 equal to T. E of C. So this is really the detailed balance as we learn it. Okay? But this equation I can massage it a bit, very, very smoothly. I can define a difference of energy, delta of E, which is E of C prime minus E of C. So I can, of course, subtract this thing from here and put it here. Delta of E. This is just equivalent. Okay? And one other thing I want to say, I'll rewrite it here, closer. I will add an index, an incrementer. To go from C to C prime, I had to increase the energy of my system by delta E. So I just write a small, subscript to remember it. It's just an extra piece of information. And to go from C prime to C, I had to remove this energy. This is not really useful, but I write it. So that's easy. Now let's consider the non-equilibrium case. Two different temperatures. What I want to convince you, and that's what I'm going to do before we finish. So now the system can exchange energies with the left reservoir at T1, with the right reservoir at T2. So we shall have something like, I'm going from C to C prime, or I can exchange nothing also. It can be an internal reconfiguration, or only with the left, or only with the right. But anyway, I can remember what I did by just keeping in my diary the moves, the exchanges I did with the two reservoirs. Okay? Yeah?
But if you just specify the initial and final state, that doesn't tell you how much energy did you exchange with each one.
So I have my initial and my final state in my Markov process. Each of one I have an energy, and I'm also keeping track of the exchanges with the left or with the right.
Okay, so for given C and C prime,
I have some
you
moves.
have different values of the
Yeah. So I prefer to think about, instead of energy, which is more abstract, particle exchange. So I have a system, I have two reservoirs for particle. Sometimes a particle can enter from the left, or can go out from the left, or can enter from the right, or go out from the right, and I keep track of all these things. Or maybe I have no exchange with the reservoirs, and just a particle rearranged in the bulk. And then the two delta E's are equal to 0. It's not finished.
Is not constant.
So it means what you mean by total. If I count the reservoirs in my game, of course it is. If I look only at my small system, it's not. I'm eating energy from the left and giving it back to the right.
The energy in the left plus the energy of the right is not constant.
Plus the energy of the system is constant. The small bar in between. So the energy here, or the total number of particles here plus here plus here is constant. The energy of the universe is constant, globally speaking. But you're again going fast. I'm coming to that. No, you're anticipating what I'm going to say. It's very nice. So can you see it, because this is an important equation, maybe in black. So the generalized detail balance, it's a bit deceptive at the beginning because this is almost what you would have written without knowing anything. But it's true. It's something like that. So it's a kind of local detail balance with each of the reservoirs. Okay?
No, I don't understand what you mean. What is delta E1?
Delta E1 is the quantity of energy that the system has taken from the reservoir R1, and delta E2, the quantity of energy that the system has taken from the reservoir E2. And the system is that. Or if you think about particles, I have a system with particles which are hopping, doing some interactions, whatever, Hubbard model, whatever you like, and I have a reservoir of particles here, a reservoir of particles here, and these reservoirs, they can exchange particles from the left or from the right. Okay? So what I claim is that this is what replaces detail balance. I'm going to argue for it, of course, in a second.
The reservoirs
Big.
remain in equilibrium, although
They are not depleted. So that's exactly what I'm going to say. You're too fast. It's wonderful. Okay. So what we are looking at in the whole description is, of course, that's exactly what I'm going to say. If we look at the system globally, S plus R1 plus R2, I include the reservoirs in what I'm studying. And the whole thing is isolated from the rest of the universe. Okay? If I look at that, and I wait an infinite amount of time, at the end, my battery will be dead, my two temperatures will be equal, or my two reservoirs would be equal. But this is not interesting. Okay? I mean, of course, at the end, you just reach a thermal state or whatever you like at equilibrium, and the two reservoirs are just totally depleted, and they're in equilibrium with each other. But I'm not interested in that. I'm interested in a sort of intermediate asymptotics, in which the two reservoirs are not modified. They're infinitely big as compared to the system. So they remain at their temperatures or at their potentials, but the system itself has reached a stationary state. Okay? But I use this trick, and this is exactly the same trick as the one we use in school in teaching when we want to go from microcanonical to canonical ensemble. So it's the same reasoning. I'm not saying that I'm doing thermal equilibrium, but this is the same trick. If you remember, to derive the canonical measure from the microcanonical, we put the reservoir plus the system in a big ensemble. We say that the configurations of the total big system are equiprobable, and we trace out the degrees of liberties of the reservoir, and we get exponential minus e over kt for the small system. So we are going to say the same. We are going to say that if we take the big system like that, okay, and we put it in a big box, and we now do a description of its dynamics. So we make a full description of the dynamics of the full system. So if we make a complete description by a super Markov matrix of this complete system, so we now take into account also the degrees of freedom of the two reservoirs. But of course, the only thing we know about the reservoirs is their energy. So the only marker for the reservoir that I have, so we now have a super Markov matrix that I write in a slightly different way, which describes how a configuration C, reservoir 1 at energy E1, reservoir 2 at energy T2, E2, goes to a different internal configuration of the small system, a different energy of the left reservoir, and a different energy of the right reservoir. And of course, I have also the opposite. So as you said just a second ago, the total energy, E1 plus E2 plus E of C, is of course equal to E prime 1 plus E prime 2 plus E of C prime. Of course, total energy is conserved. There is no creation, no destruction. So now, again, that's not a mathematical reasoning, it's a bit physical. What we are going to say, I have to put some other things here, it's not finished, is that if we do a Markovian description of the total system, because it's an isolated system with conserved energy and it's governed by Hamilton equations for all the degrees of freedom involved in the game, well, this Markovian description has to converge to a state which is a microcanonical state. Yeah? And because of Onsager, this ultimate microcanonical state will be an equilibrium, a thermal equilibrium state. So this has to satisfy, this big Markov matrix has to satisfy detail balance, because detail balance is this overarching principle that physics is time reversible with respect to microcanonical measure for the total system, measure for the whole system. For the whole thing. Okay? Which means that if I multiply these rates by the macrocanonical measure, I should have equality. So now what is a microcanonical measure? So this is exactly the same trick that we use in school to teach microcanonical and canonical ensemble. I have to multiply by the configurations, by the number of configurations of the reservoirs, and they are much bigger than the ones of the system, so I can neglect the one of the system. and here I have to multiply by. So of course here there are some approximation. It's not as rigorous as before. Now the two reservoirs, they are far apart, and we consider that they don't interact or they weakly interact. So of course this omega, I can write it as a product of two omegas. The total number of states is just a product. But we know that this omega is nothing but exponential S of E1 by definition of the entropy, Boltzmann formula, over KT1. And here it's S of E2 because they are at thermal equilibrium. And similar here with primes. And we are done. Because now if you remember, because the system is very small with respect to the reservoirs, delta E1 and delta E2 are very small. So here I will have S of I prime 1 minus S of I1. It's delta E1 ds over d E1, which is 1 over t. Am I going too fast or? Am I going too fast? Do you buy this relation? If you buy this, yeah?
Do you need to divide by KT here? Isn't that only when you do that expansion? In the exponent of S?
Oh, sorry, over K. Sorry. Oh, yeah. No, big mistake. Huge mistake. Gadol. No, of course. I'm totally stupid. Thanks. Yeah, of course. By definition, S is K log omega. And now if I just, for example, I bring the other one here, I will get something like S of I prime 1 minus S of I1 over K. And this is exponential minus delta I1 ds over di1, which is t1. And so on. Okay, I'm going a bit fast, but again, this is exactly what you do when you deduce canonical from microcanonical. The same reasoning. Okay? So if I still have a few minutes, I want to show you something.
Can you ask a question?
Yes, of course.
Why do you assume that the entire system out of equilibrium is time reversal and then equals equal balance?
What I assume is that I have a big system and it has its own dynamics, which is given by Hamilton equations. And it's totally isolated from the rest of the universe. In the end of times, it will go to thermal equilibrium. I assume that. I assume that the right Markovian description of my system should converge to the microcanonical ensemble. Because the non-equilibrium physics is for this intermediate stationary, which I'm interested in, for which I don't have detailed balance. But if I wanted to describe the whole system with a big Markov matrix, so the thing is that if you want, non-equilibrium is something which is intermediate. It's stationary, but if you wait long enough, your reservoirs will deplete. Okay? So it's just intermediate asymptotics. So it's an intermediate state. Exactly. But if I want to describe the whole thing to the end, the complete Markov matrix that describes the system should converge to the flat state for the whole big system. Okay? So that's a constraint. That's a constraint on my rates. And the constraint on the rates is precisely this one.
But that's at infinite time after you're no longer.
So that's at infinite time, I reach equilibrium for the whole system, which is a microcanonical state. But this gives me a constraint on the rates that describe the small system, and these rates satisfy this relation so that if I go to the end beyond this intermediate stationary state, I will reach a flat equilibrium. But I'm not interested in that. I just want to describe the small system after, if you want, there's a non-commutativity of limits here between the number of degrees of freedom of the reservoirs and the time. Okay? So if the time is much larger than exponential the number of degrees of freedom of the total thing, then I reach thermal equilibrium. But if it's much larger than exponential of the number of degrees of freedom of the small system, but much smaller than the exponential of the total number of degrees of freedom, I'm in a stationary state, which in fact is described by non-equilibrium physics. In some sense, I'm telling you that non-equilibrium physics does not exist. It's just an intermediate stationary thing that I'm looking at, but if I wait long enough, I will end up in thermal death. Yes, that's precisely what I'm saying here. That's precisely what I'm saying here. Yeah. Yeah. How do I know that the rates are the same? No, I agree. So what I'm trying to say is that I have a super Markov matrix which describes the whole system. And the configurations now are configurations of the system plus the reservoirs. And I try to trace out the degrees of freedom of the reservoirs and to write an effective, built on this initial super Markov matrix, I try to reduce, like reducing a density matrix in quantum mechanics. So I trace out the degrees of freedom of the reservoirs, and I want to have an effective description of my smaller system. But based on this super Markov matrix, I started with.
Is it by definition that you need to change also the large Markov matrix when you do that? I think that's the question. I mean, once you change part of the matrix, right,
yes,
a small system which is out of equilibrium, if you want to keep the whole universe energy constant or whatever, you need to manage also the values of the matrix which contains both the system and the reservoir. If not, then
yes. So somehow, what I'm trying to do, I'm taking the big Markov matrix, and I'm trying to sum over all possible values of E1 and E2, keeping C and C prime constant. So I'm making, packages with the rates. But because I have this relation which is true at the level of the embedded level, I keep this relation at the level of the small system.
A related question, just to sharpen it.
Yeah.
When I think about the time going to infinity,
yes,
is it for the little system?
For the little system.
Reservoirs are
still
so big that T1 and
T2 are not changed.
And they
Yes.
don't change.
Yes.
So
Yes.
this T going to infinity will be some type of a stationary.
It's a stationary intermediate
in
asymptotics.
between
Yeah.
the two
Yes.
reservoirs.
And I don't consider at all the depletion of the reservoirs. Yeah. So again, I completely agree that this is subject to question. It's questionable because it's not a mathematical proof. The previous one was a mathematical proof about reversibility. The thing is, I wanted to show you that something like that happens. Now, it means that your rates of going from A to B divided by the rates of going from B to A is the exponential of something. And this is something which happens to all the models I know. We don't construct them from a super big matrix, including the reservoir, and so on and so on. But all the systems, and this is exactly the point I wanted to emphasize, if I still have a few seconds, is that what we have in practice, this was a way of justifying it. But in fact, you don't really need to justify it. I could have given it to you from nowhere. Probably you would not have been happy. But it's a property. It's a property which is true for many, many processes, is that the rate of going from C to C prime is equal to the rate of going from C prime to C. This happens by exchanging some quantities, some quantity Y with some external environment, and the opposite one by exchanging minus Y. And very often, it happens. In all the cases I know, something like that is true. So now you take it from nowhere, forget about all that I said, but a way of, putting it in words and justifying it is doing that. But for example, I've been studying exclusion processes or even some Lindblad processes, and in most, or molecular motors, and in all the cases I know, something like that happens. Okay? So this is not detailed balance, because here there is no, a priori, no energy, there's no temperature, gamma is not 1 over kT, but you have this ratio of the forward by the backward is exponential of something. Here, Y is not energy and gamma is not temperature. It's a property. Well, no, here, for example, I have 2 different temperatures. In equilibrium, it would be the temperature, but what I claim is that in many, many Markov processes out of equilibrium, such a relation is true. Out of equilibrium, such a relation is true. Whether it's coming from here or coming from somewhere else, who cares? But detailed balance is broken, but not in an arbitrary way. It's broken like that. Yes?
If you're looking at non-Markov systems that you study, do you see a different dependence?
So, if you look, for example, at a Langevin system, you have an equation which replaces that, for example. It's a slightly more elaborate, but you can write it. If you have systems with kernel, again, if the kernel is well-defined and finite, you will have some convolution relation with the kernel. If you take a totally general system, I don't know. But
there is an assumption here that the Markov matrix is independent of time.
Yes, so you're right. It's a very good question. There's an assumption that the Markov matrix is independent of time to do time reversal. You can generalize time reversal to time-dependent Markov matrices. Then you will have a process, okay? And then this thing may start depending on time too. So I'm trying to put things as simple as possible, but there are plenty of generalizations. Yes, we'll come to that next week, tomorrow. Yeah. This is extremely interesting, and we'll do that. Of course.
That's related to the large deviation?
That's related to linear response. Yes. You can recover a linear response in the case you linearize the difference. Do I still have a few, maybe 2 or 3 minutes? Yeah, I want to conclude now. Yeah?
In this case, it amounts to the fact that the reservoirs are large, in a sense, right?
Yes. Yes.
Right?
Yes. That the reservoirs remain in equilibrium, unchanged, at least, stationary. So here I don't have any entropy. But
in this case,
yeah.
The exponent appears.
Because the entropy is because I broke omega E1 E2 as omega E1 times omega E2, which is the additivity of entropy, clearly. But maybe I should rewrap it. I don't know if you're not convinced by that, I'm sorry, but this was kind of long argument, hand waving and physical. But believe me, in many, many concrete systems, detailed balance is replaced by that, without having to put everything in a big reservoir or in a big ensemble. It comes for free, okay? But this is the thing which comes for free very often. And just a second. And this is very nice, because now that I removed everything, now we can redo the reasoning we did here, taking the ratios, okay? So if we take the ratios, so I just leave it as an exercise, because this is exactly the same reasoning, you will find, so now when I go from C1 to C0 to C1, I put some Y1 here in this abstract thing, Y2 and so on. And if you use this instead of detailed balance, but this is something, it's better than nothing. Okay, we had detailed balance, now we have this thing. So we can do the same reasoning, and we can compute the ratio of the probability of having C of t, a trajectory, divided by the probability of having C hat of t, the reverse trajectory. It's not going to be 1, because we have this incremental factor which destroys everything. Not everything, but some things. We shall have exponential gamma 1, y1 plus y2 plus yn, p stat of C0 divided by p stat of Cn, which will not simplify. So you see, it's not the zipping process that I had, but just the ratios. which will give me that. But if I call Y the total current or the total energy exchange with both the reservoirs and the sum of the Yi's, I essentially have exponential gamma 1Y, the ratio of the two stationary probabilities. And this has a very nice physical interpretation. This tells you that, of course, it's not equal to 1 anymore. Yeah? But this tells you that the bigger Y, but what is Y? Y is a kind of current. Okay? Is the energy you take from the left, or the energy you give to the right, or the particles you take from the left. So the bigger the current, the more you break reversibility. Okay? In the ultimate case, when this is almost of order 1, if this is 0, it's almost reversible. So the current, Y measures irreversibility. Okay? And somehow, if you take now averages, and I will end here, I will take it back maybe next time or wrap it. If you take averages, this tells you that the average of exponential gamma 1y is really a measure of irreversible behavior. And this is the essence of Galois-Cohen theorem. That from here it's a few minutes proof, and then we shall use that theorem. We shall take it as granted out of equilibrium. Okay? It's just one proof, but there are certainly half a dozen proofs now in different contexts, totally different ones. For example, chaotic dynamics, which has nothing to do with Markov systems, nothing to do with physics, nothing to do with reservoirs. I mean, it's just purely mathematical. And we shall take this Galois-Cohen relation as something solid and exploit it for some concrete cases.
Maybe you call it current. It's delta E or delta particle, not delta E dot. Right?
It's a total. So you're right. It's in my jargon. It's a time-integrated current. I always call it current. It's the total energy. So it's the time. Thank you very much. In our community, we call it current, and this is a mistake. It's total charge, not the current, but time-integrated current. Thank you very much. You had a question.
Yeah. What does the subindex 1 denote in the gamma?
Yeah, it means nothing. But if I had 5 more minutes, I would have taken a Laplace transform of this equation, and the Laplace variable I take is gamma. So that I would end with some gamma plus gamma 1 and gamma minus gamma 1 and not gamma plus gamma. That's the reason. But I'm too short of time. I need to take some Laplace transform now on this equation.